We're working on finding zeros of polynomials. We've done this quite a few times now, and at this point you should be able to find pretty much all zeros of polynomials. But I have one more example that's a little bit unique than any other example that I've given you so far. So this example is x to the fourth minus 6x cubed plus 28x squared minus 18x plus 75. Now it gives us one of the zeros. It tells us that 3 minus 4i is a zero, and so it's asking us to find the remaining zeros. Now we know that since this is a degree 4 problem, that we should have 4 zeros total. It gives us the first one, so that means when it asks us to find the remaining zeros, we have 3 more zeros that we're looking for. Now in the last few examples, I've told you to graph this on the graphing calculator first, and then kind of get a guesstimate of what your zeros are to come up with. So I have substituted this into my y equals, the same equation there. I have plotted it on the window where my x values are going from -5 to 5, and my y values are going from -50 to 200, where my y scale is 25. And so when I graph it on this window, it looks like this right here. Now remember, zeros are the same thing as x-intercepts of the problem, and so when I see this graph here, I don't see it intercepting the x-axis at all. So that should be an indication right away as to what form all of your zeros are going to take. Remember, I told you if it doesn't cross your x-axis, that your zeros are going to be imaginary. So in this problem, I'm going to have 4 imaginary zeros. Now they gave us the first one, which is a huge hint, because then that tells me where to start with this problem. So I'm going to start the same way that I did with any other problems. I'm going to do this by synthetic division. So when I set this up, I'm going to use the coefficients that I see up here because I'm not missing any terms. I'm going to leave myself some extra room in between, and I'll show you why in a minute. And the thing that we divide it by is the zero that they actually gave us, 3 minus 4i. Okay, so now I'm going to run this through my synthetic division. I bring down my first digit and I multiply. 1 times 3 minus 4i gives me 3 minus 4i. And now I add these, but I can only add like terms, so I can only add my real parts. -6 plus 3 gives me -3, and then my -4i carries down. Okay, so now I need to multiply these out. I have 3 minus 4i times a -3 minus 4i. So first gives me -9. Outside gives me a -12i. Inside gives me a +12i plus 16i squared. So when I simplify this, my -12i and my +12i cancel out. My I squared I know is the same thing as -1. So this gives me 16 times -1, which gives me -16. And so when I combine -9 and -16, that gives me -25. So that's what goes up here. Now I add 28 minus 25 gives me 3. And now I need to multiply. I have a 3 times a 3 minus 4i. So distributing that through gives me 9 minus 12i, and so that's what goes up here. So combining like terms here, that gives me -9 minus 12i. All right, now I have to multiply this again. So I have 3 minus 4i times -9 minus 12i. So if I FOIL, that gives me -27. Outside gives me a -36i. Inside gives me a +36i. And last gives me a +48i squared. Well, my inside i's cancel. This turns it into a -48 back here. And so I have -27 minus 48, which is the same thing as -75. And so that's what goes up here. And so when I add these last two terms, I get 0. And I knew I should because it told me that this is a 0. Okay, so I've simplified this a little bit, but it doesn't look like I gained much ground here. All I did was confirm that 3 minus 4i is a 0. Well, we've learned that if they're imaginary numbers, that they need to come in pairs. So if 3 minus 4i is a 0, that also means that 3 plus 4i is a 0. So I need to take these remaining terms here, and I need to do synthetic division with them with my other 0, and I need to figure out what I end up with there. So let's try this again. Let me get rid of all this scratch work down here, and let me set up another synthetic division right underneath of it. But now I'm going to divide it by my other 0. So setting up my second synthetic division, and this time I'm going to divide it by 3 plus 4i. So this is a good time to point out that if you know your zeros, you need to use a new one each time, unless it guarantees you that you have a multiplicity of your 0. Doesn't say anything about that here, so we need to use an alternative 0 than what we started out with. So let's try this again. Setting up my synthetic division, bringing down my 1, multiplying gives me 3 plus 4i. This one's a lot easier because everything cancels out, leaving me with 0. 0 times anything is just 0. So when I add these, that gives me 3. And when I multiply them, 3 times 3 gives me 9, and 3 times 4i gives me a positive 12i. And so that helps because, again, everything cancels out to be 0. So when it says find the remaining zeros, we know that we have 2 of them done so far, and this one down here has to give me 2 more. Now, I started with an x to the 4th. When I ran it through one synthetic division, that gave me x to the 3rd, moving 1 degree less. And when I ran it through my second synthetic division, that gives me x squared. So the polynomial factor that I have left is a 1x squared plus 3. So I need to set that equal to 0 to find my remaining zeros. So it gives me x squared is equal to negative 3. Force in a square root, which forces in plus or minus. And so that gives me x is equal to plus or minus square root of 3 times I. Now, by the graph, we knew that these had to be imaginary numbers, so I came up with all of my imaginary numbers here. 2 of my zeros are positive root 3i and negative root 3i. And then my other 2 zeros, one I knew because the conjugate theorem, 3 plus 4i, and the other one was given to us, 3 minus 4i. So find the remaining zeros, or all of our zeros total are 3 plus 4i, 3 minus 4i, positive root 3i, and negative root 3i. And now last I need to factor this into linear factors. Well, I use the same principle that I've been using pretty much on every example. If something's a 0, then x minus it is a factor. So all I need to do is subtract these from x's then. So I have x minus 3 plus 4i, x minus 3 minus 4i, x minus square root of 3i. Remember, the I does not go underneath the square root, so if you need to write it in reverse order, that's okay. And x plus square root 3i. And so now we have factored it into our 4 factors. Degree 4 polynomial, 4 zeros, 4 factors. And so we have tackled this unique example of having only imaginary zeros.